Hi everyone, I am Sir Mel and welcome to Mathematics in the Modern World. If you are new to my email channel, please don't forget to subscribe and click the bell button for more notifications. Our lesson for today is about the different types of sets in mathematics. But before we're going to discuss it, let us take a look back about the set. When we say set, it is a collection of well-defined objects that contains no duplicates. And it is best described using the braces. So whatever you put inside the braces are what we call the objects of the set, or also known as the elements of the set. The elements of the set should be unique, distinct, and the order and arrangement are not necessary at all. Now let's get started with the different types of sets. Shall we start with the empty set? In a simple sense, empty set has no element at all, and it's best described with these two symbols, the null set and empty set. Now I have here two examples. Read as set P has the set of all x such that x is a leap year between 2016 and 2020. We have also set Q has the set of all y's such that y is a whole number which is not a natural number, y is not equal to 0. These two examples answers are both empty set or null set. How? When we say leap year, these are the years that are both multiples and divisible by 4. 2016 and 2020 are both multiples and divisible by 4. So therefore, these are the two leap years. However, those years 2017, 2018, and 2019 are not both multiples or divisible 4. Hence, P is an empty set. Now, in discussing the second problem, let us try to recall our topic about algebra, about the set of real numbers rather. So, let us have this diagram. Set of real numbers are divided into two subsets. We have capital I, that is irrational, capital Q, that is rational. When we say irrational numbers are numbers that cannot be expressed as the ratio of two numbers. And these are the examples of it. We have pi, e, square root, whose radicands are not perfect square. On the other hand, we have rational numbers, are numbers that can be represented as a fraction or ratio. Under the rational numbers, we have capital Z for integers from negative 0 to positive infinite. We have W whole numbers from 0, 1, 2 to positive infinite. And last is the natural numbers, or also known as the counting numbers, starts from 1, 2, 3 to positive infinite. Now, these are some of the basic concepts in order to fully understand the second problem. So let's go back to the second problem. Okay, as you can see, that whole numbers are all natural numbers. However, natural numbers are not all whole numbers, since 0 is not a natural number. So in this case, Q has an empty set or null set. Okay, so let's now proceed to the next set, and that is singleton. When we say singleton, it has exactly one element. Now let us have these examples. We have set A has a set of all x, and such that x is an even prime number. And we have set B has the set of all y's, such that y is a whole number which is not a natural number. Now when we say even number, these are the numbers that ends with 0, 2, 4, 6, 8. Or we have also odd numbers that ends with 1, 3, 5, 7, 9. Those numbers that can be factored by 1 and itself is what we call a prime number. Otherwise, we call it as composite numbers. So in this case, our answers are both singleton. Since we know that 2 is an even number, at the same time, 2 can only be factored by 1 and itself. Now on the second set, we have know that all whole numbers are also natural numbers except for the 0. So whole number has a 0 and natural number starts from 1 to positive infinite. So therefore set B has an element of 0, which is also now a singleton set. Now let's proceed with a finite set. Finite set means can be counted or terminates at a certain number or word. So let us have these two examples. We have set A has the set of all x such that x is a month in a year. We have also set B has a set of all y such that y is the zero polynomial equation x to the power 4 minus 2x cubed minus x squared plus 2x. Now, the answers are here. We have 12 months, we have 4 zeros. On the set A, we don't have any problem since we know in a year there are 12 months, starts from January, February to December. But on the second set, we need to recall our topics about algebra. And I have prepared a slide to explain how we able to get the 4 zeros. Okay, so in order to solve the zero polynomial, we need to recall the factoring. And these are some types of factoring. We have the GCF, greatest common factor, grouping, difference 2 square, sum or difference 2 square, trinomials or perfect square trinomial, and the general trinomials. Now, in order to solve these zeros, we need to use these sum of the factoring ideas. So let us now try to do the solution. First, of course, we need the given. Now, evaluate all the variables in a given equation. We're going to use the factor out. So, since x to the power of 4 can be factored out by x cubed, so we're able to multiply x cubed to x to make it x to the power 4. And we have also x to multiply by x, it becomes x squared. So we have now the factors. So by GCF, we have x cubed times x minus 2 minus x times x minus 2. Now evaluate this new equation. We notice that there is the same factor x minus 2, x minus 2. We're going to group them as 1. So we have x minus 2 and combine x cubed minus x. So we have now the third equation. So in this case, the objective of getting the zero polynomial is to make all the degree of x into 1. So x minus 2 has no problem, but x cubed need to convert it or reduce it into x to the power of 1. So we're going to do again factoring, and the best way is the GCF. So since x can be factored out from x cubed, so we're going to use the x. So we have now x minus 2 times x squared minus 1. If we're going to multiply x by x squared, we get x cubed. If we're going to multiply x by negative 1, we're able to get negative x. They are the same. So in this case, still the degree of the x, or one variable of here, x, is still not equal to 1. So we're going to apply the next factoring, and that is the difference in two squares. Okay, since 1 is a perfect square, therefore we can multiply x minus 1 by x plus 2. It also has a product of x squared minus 1. So in this case, we're able to see all the zeros of polynomial by equating all the factors into 0. Okay, so we have x minus 2 equals 0, x equal to 0, x minus 1 equals to 0, and x plus 1 equals to 0. By transposition, we're able to get x equals to 2 from x minus 2 equals 0. We have also x equal to 0, at is. We're able to get x equals to 1 from x minus 1 equals 0. And we're able to get negative 1 from x plus 1 equals 0 by transposition. Now we have the different zeros of the polynomial, and we have 4 zeros. That makes the set B will have 4 zeros. Now let's proceed with the opposite of the finite set, and that is the empty set. Okay, if a given set is not finite, then it will be an infinite set. Let us have these two examples. Set A has a set of all x such that x is a natural number. Set B has the set of all y's such that y is the ordinate of a point on a given line. So we know in our previous presentation that natural numbers starts from 1, 2, 3 to positive infinite. So that makes it as infinite set. The set B is about the Cartesian plane. Those points found in the x-axis is what we call the abscissa. And those points found on the y-axis is what we call the ordinate. And we know that ordinate is being extended upward, that is positive, 0, then downward to negative, infinite. So that makes them infinite set. Now let's proceed with the subset. Subset means if a set A contains elements which are all the elements of set B as well, then set A is known as the subset of B. To have a clear idea, let us have these examples. So set A would be the original set whose elements are 1, 4, 3. If we produce another set from this original, we call it as subsets. That's why we have set A has subset, singleton sets 1, 4, 3. We have 1, 4, 1, 3, 4, 3 elements, and we have the same from the original 1, 4, 3 elements. So these are examples of subsets of A. Now, let us use this given to identify the types of subsets. Okay, so we have this first produced from the original, we called it as the proper subset. But if the new produced set is the same as from the original set of elements, then we call it as improper subset. I hope you have a good idea about subsets. Now let's proceed with the cardinality of the set. Cardinality of the set is the number of distinct elements belonging to a finite set, and it is denoted by n of the set A, or read as the number of cardinality of set A, or card of A, and the absolute symbols of A. Now, in a simple way, cardinality means you're going to calculate the number of distinct and unique elements in a given set. So let us have these examples. Okay, find the number of cardinality from the letter of the word scology. And also find the number of cardinality in the set A, in the set of prime number less than 15. So since there is a word scology, we're going to list down all the elements, the letters. So since it must be unique and distinct to each other, so we have now S, C, H, O, L, G, Y. Count them individually. So we have the number of cardinality of set A is 7. Now on the second set, we have prime number less than 15. First, we need to know for the list of prime number less than 15. So we have 2, 3, 5, 7, 11, 13. Count them individually. We have number of cardinality of set B is 6. If we have another example, let's say find the number of cardinality in choosing a month in a year. So the number of cardinality is 12. Since January, February, March, count them all, we have 12 months in a year. If we're going to choose a day in a week, we have 7 number of cardinality from Monday, Tuesday down to Sunday. So that is how we're going to get the number of cardinality of the given set. Now let's proceed with the power set. Power set is like a subset. So you're going to reproduce or generate subsets from the original set. Let us have this example. Set A has 1, 4, 3 elements. Then the power set of set A will be empty set, singletons 1, 4, 3, elements 1, 4, elements 1, 3, 4, 3, and the same elements to the original. We have also, if set B has the elements of EX, then power set of B will be null set, singletons EX, and we have elements EX. So if we're going to combine the cardinality to power set, we have this. find the number of cardinality of the power set A and the number of cardinality of the power set B. So if we're going to count all this power set in the given set A, we have 2, 4, 6, 8. And we have 4 on the second set. Now, what do you think would be the basic formula in order to know the power set at the given number of cardinality of the given power set? Simply, we're going to follow the formula 2 to the power of n. How? On the given first set, we have 3 elements. So you're going to substitute n to 3, it becomes 2 to the power of 3. And 2 times 2 is 8. The same as in the second set, set B. So we're going to change the n into 2 because there are 2 elements. So 2 to the power of 2 is 4. So I hope you able to use the formula for the power set in getting the number of cardinal of the power set as 2 to the power of n. Now let's proceed with the equal sets. From itself, the new set should be equal to each other. Example, if we have ACT, then the other set must have the same elements, CAT, TAC. As you notice that the element is just reshuffled. So since according to the characteristic of the elements should be unique, distinct, and the arrangement or order is not important or not necessary at all. So we have the equal sets. But if the other set has like this ACT and we have ACTO or actor, obviously they are not equal. So in the next set, we have if set C has the elements of all x such that x is a letter in the word book, so distinct and unique, we have BOK. Then BOK, of course, is not equal to BOT. However, if the set has BOK and the other has KOB, then they are equal set. Let's proceed with the equivalent sets. Now, to be equivalent, the sets should have the same cardinality. So, meaning to say, it's not about the elements, but it's about the number of elements. So, we have here two examples. If the set of P has the elements of 1, 4, 9, 16, 25, we count them individually, that is 5. And the set Q has the elements of 1, 2, 3, 4, 5, still 5. So they are equal. That makes them, equal in number, so that makes them equivalent. The second one is if P has the names of Darrell, Frank, Lorinel, Reggie, Benjay, they are some of my close friends, and set Q has the elements A, E, O, U, that is the vowel from an English alphabet. If we count them individually, we are able to have 5, the same 5 number of cardinality. So that makes them equivalent sets. So we can tell that all equivalent sets, all equal sets are equivalent sets, but not all equivalent sets are equal sets. I hope you understand that. Let's proceed with the universal set. When we say universal set, it contains all the elements, particularly in a given situation. So, an example, if we have a universal set refers to a month in a year, so we have the universal set from January, February, March down to December. They are all our universal set. If we have a universal set of counting numbers less than 9, so we have a universal set from 1, 2, 3, 4, 5, 6, 7, 8. If our universal set refers to the vowels in an English alphabet, so our universal set is from A, E, O, U. Okay, so that makes the universal set. And the universal set is denoted by capital letter U. I hope this time you have a clear idea about universal set, and that ends the different types of set. Now let us proceed to the operation on sets. Operation on sets were made up by the German mathematician in the name of George Ferdinand Ludwig Philipp Cantor, or also known as George Cantor. Now let us have the four operations on set. So first is intersection is denoted by inverted letter U. We have also union denoted by U, and the difference denoted by the symbol from minus or subtraction. And last is the complement, the prime, or the word AC. Now, let us have example about it. So when we say union, the keyword is to put them together, combine, or to unite. Let us have this example. We have universal set 1, 2, 3, 4, 5, and the set A has elements 1, 2, 4, set B has 3, and set C has 5. We're going to find set A union to set B. So since the keyword is to combine, so we're going to combine the elements of 1, 2, 4 to the element 3. So we have now the set A union set B is 1, 2, 3, 4. In symbol made by John Venn or Venn diagram, as you observe that the set of A and set of B are all shaded region. Now let's proceed with the intersection. Intersection keyword is to see the common element or elements of two or more sets. So let us have this example again. Universal set 1 to 5. We have single tone set A, which is 1. We have set B has elements of 3, 4, 5, and set C has an elements of 1, 3, 5. So we're going to find the set B intersect to set C. So the keyword is their common element or elements. Now, what do you think is the element present in set B that is also present in the element or elements on set C? So we have 3 and 5. Therefore, our answer is 3, 5. In diagram, we have set A, set B, and the only shaded region is in the middle. That is intersection. Let's proceed with the complement, the prime, the AC, which means to complete is the keyword. Now let us have an example. We have given universal set 1, 2, 3, 4, 5. We have single tone. Set A has one element, and we have also set B has 3, 4, 5, and set C has 1, 3, 5. We are going to find C prime or complement of set C. So again, the keyword is to complete. By completing the set C, we're going back to the universal set. Since set C has an elements of 1, 3, 5, so there are only two elements to complete them from universal set. So we have that 2 and 4. So the answer of the C prime or complement of set C is 2, 4. In diagram, we have observed that the shaded region is outside from the set C or shaded region at the universal set. The last operation on set is the difference or set difference. So the keyword is different. You're going to see what is different on the first set that is not present on the given another set of elements on the other set. Okay, so example, we have given universal set 1, 2, 3, 4, 5. We have set A has 1 and set B has 3, 4, 5 and set C is 1, 3, 5. Find the set difference of set B different to set C. So again, we're going to see the elements from set B which is not present on the given elements on the set C. So since set B has 3, 4, 5 and set C has 1, 3, 5. So 3 and 5 are present on set C. Therefore, there is only one difference from set B to set C, and that is 4. In diagram, we have the set A shaded region, but the middle as well as all the set B is not shaded. That makes them set difference. And this is the last topic about the different types of sets. Thank you and God bless everyone.